Yeah. All right. So welcome everybody. This is going to be the class on intelligent agents and active inference. It's going to be the last class where we introduce new content, at least for the exam. So next week there will be a probabilistic programming session and a class by Magnus on what is life. That's going to be a fun class, but not going to be on the exam. This class is, but as you may have noticed, this class is more conceptual. I mean, we're talking here about stuff that is highly under development in the neuroscience community, also in the engineering community. But there are no engineering books on this yet. So I just want in this class for you to kind of get an outlook on where all this stuff on probabilistic modeling, the probabilistic approach to machine learning, where it can lead to. And the difference of this class, let's say with what we've done in the past, is that now we call it, this is a class on intelligent agents. And before that, we were talking about machine learning. And just very roughly, I think machine learning is about you have a data set, you build or you propose a model and you update the parameters of that model based on the data set. But here it's different. Here we talk about intelligent agents. So this is AI, and we need to talk about what is intelligence, right? And well, there isn't any very agreed upon definition for intelligence. But I think that, okay, what separates intelligent people from less intelligent people? Well, intelligent people make better decisions. And how do they do that? Well, why is it difficult to make a good decision? Well, the future is uncertain. You will not know what the consequences are of your decisions. And so it turns out that how is it that intelligent people can make good decisions? Well, the brain actually is a generative model for your sensory inputs. By sensory inputs, I mean inputs through your eyes, your ears, and actually also from your organs inside your body. It needs to regulate your body as well. And with that generative model, the brain can actually can make predictions. We can play that model or run that model forward in time, right? If I want to cross the street and there's a car like 50 meters away, before I cross the street, I run a model of the environment forward, and in that simulation, I see the car approaching and me walking, and if the car doesn't hit me, then I will cross, and if I think there is a high chance the car will hit me, then I will wait. So we use these generative models of the environment by running them forward, and then sort of deciding if we run it forward, does something desirable take place or something that we don't want, right? Do we stay alive if I take a certain action? So and then we take the action such that the desirable scenario will roll out. And we can model that with basically with everything we've done so far. I will try to share my screen. Let's see if that works. Okay, I'm not sure if you can see this. Maybe I can try to make it a little bigger. No. Okay, so let's say here's just the world, R of T. We can take actions onto the world. That's just our behavior. You make the action or a decision to cross the street or not, and that action leads to, well, it's stuff that happens in the real world, and it leads to new observations in my eyes and in my muscles, and so new observations. Everything in here is basically my brain. And what the brain has is a generative model of how the world works. So let's assume that we model the world by a state space model, as we did in the last class. So there is an internal states, and there's an S, and there are state transitions, and the states of the world lead to observations X of t. X of t here is really the same as Y of t. It's just that Y of t is something that lives in the outside world, and X of t is a variable in my model. In the same way, actions is basically, let's say, actions in the frame of reference of the external world, and U of t is a variable, a control variable in my model. But in the end, they're going to be the same. I just want to distinguish between variables that live in my brain and if you will, variables that live in the world. But here, this is basically my model for the world. And this this diamond like shape means I've chosen an action. So that's basically an observation, but then it's a selected observation. So it's not the same as an observation from the outside world, which we will denote with a black square. So at this point, I've chosen an action, and action could be take the first step. And so in the real world, that leads to a new observation. And now I am interested in what is my next action. So what we do is we roll out this model to the future, and in the future we will take new actions, and we can select certain sequence of action here, and we roll out, and then, well, we will generate xt plus 1 and xt plus 2 and xt plus capital T by just rolling this out to the future. Now, the essential thing is that, let's say that the brain is also capable of putting in sort of priors on desired future behavior, right? What we don't want is that the car is going to hit me. So there's going to be, I'm going to encode that here in a very low probability. I'm going to encode here a very high probability for observations that are consistent with not being hit with the car. Then what we'll do is we basically just do inference in this model. So we pass messages back, and we pass messages here from the future back to this action, to this new action U of t. So what is this action? This is going to be the action that is most consistent with basically these desired outcomes. So I will choose now the action if I then, let's say, is going to be a posterior probability, and I will select, for instance, the one with the highest probability is going to be my next action. I will move that to the world and I get a new observation here, and then the process returns. And all I do is I just keep rolling, say, my generative model of the world forward and extending it with desired observations or probability distributions over desired observations. And that is enough. And if we now can do inference for the next action, I can just run this process. And the better I am in predicting the world, the better my decisions will be. And it will look like to the outside world that I'm very intelligent. But all I'm doing is I just have a good model of the world, and I am capable of setting priors that correspond to good outcomes. And I'm good in inference. I'm good in inferring what the next action will be. So this is the sort of the scheme. And what's interesting about this scheme is you don't see really utility functions or reward functions. It's just a probabilistic model, like any other, everything we've done before. It's a dynamic model that we roll forward in time. We do inference for states, but they happen to be control variables, and that's all we do. And in this way, you can build systems that, well, that behave, because we observe behavior by basically by the actions that somebody takes. We can build systems that behave in a purposeful and yeah, intelligent way. So that's the idea right? So then you can make it, of course, I mean, you can ask, okay, where do these priors come from? Well, the idea is that there are that these kinds of models are nested, and it's a higher level module that will set, basically predict the priors, right, for the next outcome. But that's not really something for this class. So that's the basic idea of how you can design an intelligent system by everything that we've done so far, by basically building a generative model here, extending that model with a goal prior, an extra probability on future outcomes. And in this model, I'm going to do inference for you at t+1. And that's it. So it's just inference in a probabilistic model. That's all that's needed. So with that, I'm going to undo the screen now, and I'm going to leave it also at that for now and invite you to come with questions. All right, so Gutan.
Yes. Hello, Professor Bird. Am I audible?
Yes.
Yes. Yeah. So this is a very interesting lecture, and the one. So I haven't yet still fully understood the idea, but the one doubt that I want to discuss with you was in the part where we explain about the recursive nature of it. So if you can go to that diagram, that would be really helpful. The second last diagram, which talks about the future predictions, flowchart kind of a thing.
Yeah, just a second. All right. And now
Yes, yeah, that one.
so the bottom one, this?
No, the one just before that.
This one.
Yes, yep.
Okay, yeah.
Yeah, so in this diagram, I understood the basic idea of it, of how we have the model parameters and how we infer the future observations. And since this is a recursive kind of a model, there is this kind of a chicken and egg problem, right? Like, so my question is like, how do we set this into motion? So for example, for the current state T, we have a previous state input coming in, right? Which is actually used to infer the next state model. So how does that how do we estimate that ST minus 1? Is that based on like a prior probability assumption that we take, or I found that a bit that aspect a bit vague. Could you, if you explain that a bit further, that could be helpful.
Yeah, so maybe I can go up to here. So the idea is that I mean, we're going to model the world by a dynamic model with latent variables. That means there are going to be three types of variables here. There's going to be actions that I make, and that will affect the outcomes or the observations that I make. For instance, if I turn my head, then I will observe different things, right? So the actions will lead to different observations. And then the world itself, I don't observe everything that's going on in the world. There are all kinds of mechanisms going on that I do not observe. And we represent all these let's say, all the causal structures and the structure of the world with just a latent state space S or S tilde here. And now we build a model for that. So there's going to be, basically we say the model of the world is going to be, I make actions, my actions change the dynamics of the world. And then, yeah, depending on the sensor that I have, do I have an eye or an ear, and what is the position in that world? I make different kinds of observations X. But so do you see these three types of variables? Actions that I make, internal states of the world, just everything that's going on in the world, and then, yeah, based on the sensor that I have, I make some observations. And the idea now is, so this is basically a model in the forward direction from actions to observations, just like how the world runs. But when I get observations, yeah, I run that model backwards and run the model backwards. So from my X, I first infer S, and what are S? Well, they're the causes of my observations. You can think of it as your perception of the world, right? I look now outside, I see buildings there. Yeah, let's say the observation of me seeing a building outside is caused by the fact that there is a building there, or at least I hope so. Right? So there is an external world, and there is a cause for the fact that I actually see a building, but what I see is just a state in my brain here as that's just my perception of the real building that's out here, right? So this S is sort of a representation in your brain or a distribution or a set of variables that represent, yeah, the fact that there's a building outside here or there's something else going on. So S is your, let's say, your posterior distribution over S is what we sort of equate with perception. That's our understanding of the world. And U are we also then infer U, and U are the controls that I have on that world. I can walk towards the building. I can look into another direction. Maybe the building makes sounds and I can listen to it. So you are let's say the controls that I have, and that's how we kind of model it. So think of S as your perception of the outside world. You can also think of this as the causes or the causes of your observations. Is that sort of understood?
Yes, that is understood. But one follow-up question would be, so I understood how the observations help us infer the state and in effect the actual action that comes up. So my question is, like, if we say if I'm designing a bot for like the video that we showed, the self-parking bot, right? So while I'm designing this model, so in this graph, I understood that I get observations xt, which can be used to infer st, and also we also have the actions ut, right? And these together help me infer a future state and hence a future action and so on and so forth. So here, what exactly would be st minus 1? The first st minus 1. I know that for st plus 1, we would have like the current state as the previous one. So, but for st, what is the st minus 1? I think that is something that I'm a bit confused.
This would be, let's say that S of t would be the position. Your estimate st would be the position and velocity of the robot.
Okay.
And so what this would be a model for is that, okay, a U of t would be, let's say, some kind of extra power or I mean, you press the gas pedal, right, in your robot. And then this model, the transition is how does the position and velocity change of the robot if I press a gas or if I do something to that to that robot, right? If I pull a lever or press a gas pedal, then the position and the velocity changes, right? There's going to be some acceleration, and that then so by making a particular action, the state of that robot changes from st minus 1 to s of t, and then I make a new action. And so what then happens is then I make an observation in the world, and there could be some kind of, yeah, maybe let's say the world, my model may not be perfect of the world, right? So I make a new observation of a noisy observation of position, and that may not entirely correspond to my prediction. Okay, well then through this model, the likelihood, I can kind of make a correction on what the new position and location of the robot is. And so now I'm here. Then I make a new action that's going to be by inference. I'm going to like give a little bit or break maybe a little bit. I make a prediction on what's going to happen to that robot, the new position and velocity. I make then a new observation and I correct my prediction. And so this is how I go forward. Right. So I use actual observations to make corrections to my predictions and basically to estimate what is the state of this robot, where is it located and where is it going, right? Because I need that. Yeah, I need to model the world because in the end I want to have an observation here that I'm parked in some parking lot or something, right? And as long as that's not the case, as long as my prediction for X of t in the future doesn't match where I want to be, then that will translate in, well, basically means there's still free energy here left over. There isn't a good match between the prediction, there's still prediction errors, if you will, and that will lead to new actions until my predictions are that, yeah, I am where I want to be. So then the actions, there's no more prediction error and the Kalman gain will become 0 and you're not going to do updates anymore.
Yes, got it. Yeah, that
Okay.
makes sense. Yeah, thank you.
Okay, I want to go to a question I saw in the chat, but this is a very good question by Mike, and let me see if I can read that question. Oh, I don't see it now. Okay. How is searching, as mentioned in the video of Carl Friston, represented in the active inference model? So it's a really good question. So what Carl Friston talked about is, let's say you're an owl and you're hungry. What are you going to do? Well, you're going to fly over the earth, and then you're going to search for something to eat, like a rabbit or whatever. Right? Well, an owl doesn't eat a rabbit, but something small that you can eat. And then once you spot it, then you go down and you go get your little animal, whatever little mouse, let's say. And so why does it start searching? And in reinforcement learning, we call this exploration versus exploitation. Exploration is basically you are searching for something, and then when you have found it, then you exploit that knowledge and do what you really wanted to do. Let's say if you ask me to go for dinner tonight to a restaurant, I might respond, well, let me check my fridge. So I'm first exploring what are my options. And if my fridge is empty, and then I'll say, yes, I would love to go to dinner tonight with you. Right. So I don't answer immediately yes or no. Because at that time when you ask me, I feel, well, there is still some uncertainty that I need to resolve. Namely, do I have something in the fridge that goes bad? And then I just may want to finish that. Right. So I first resolve some uncertainties that I have. Then I make the decision. And it's the same thing really in when you cross the street, right? You take a look and you do that that you do that computation of in the future, simulation in the future, is the car going to hit me? Now suppose that that computation actually doesn't make you very confident yet that the car is not going to hit you. What do? Well, you actually wait and you take another look. You gather more information. You explore. You want to, right? You take a second look and say, okay, now the situation is clear. I have more information. Now I will make the actual decision, right? So it turns out all of this is really part in the what we call the expected free energy. And you can simply think of as the expected free energy as basically the free energy that is in the future of the model around here, right? I mean, there are computational details, but just think of it as you know the free energy is basically an upper bound on log evidence, and log evidence is log of the probability of the observations given the model. Well, we can extend this in the future and put let's say priors on it, but that doesn't change the number of observations. So the whole thing, even if I run to the future, will still be an upper bound on log evidence. But just this part about the future is, yeah, we call it expected free energy, and I can make a decomposition just like we did the decompositions before between, let's say, accuracy and complexity, and energy and entropy. If we formulate expected free energy, and then we do a decomposition, we can do a composition that will translate into explorative behavior, exploration, and exploitative behavior, goal-directed behavior. That's sort of the beauty of the framework. You don't need to do anything for it. It's completely transparent. Just by minimizing free energy, basically it means if you have a really good model for the future and you enroll this, then so if you are accurate about if your predictions are accurate, then you will be very goal driven. You will right? Then you will compare the future that you predict to your desired future and base your actions on that, and try to minimize the difference between the expected future and your target future. However, if your model is not yet very good, right, your model of the environment, well, then your predictions are unreliable. So it doesn't make sense to compare your predictions to where you want to be and base your actions on that. Then your actions should be such that you want to actually collect data in the world that will train your model of the world better. That we call exploration. And you don't have to do anything for it. It's all part of the framework. So we don't think about, when we behave, about whether we do exploration, explorative behavior, or exploitative, goal driven. It's completely transparent. If your model is not very strong yet, your actions will be aimed at collecting the data that will train your model. And once you have a good model, well, then you can predict the future accurately. You can compare it to where you want to be, and then you can make actions that fulfill your prediction, or that fulfill your let's say your where you want to be, right? So it's this is one of the major strong points of the whole framework. In the optional slides, we talk a little bit about that mutual information and say, okay, goal directed behavior and epistemic, because epistemics means it means knowledge, or knowledge seeking, inquiring, right? So this is about the exploration term. You don't have to know this. We're not going to. I'm not going to ask you about it, but it's a really good question, so thank you for asking it. It's one of the major points of attraction of this framework. It also there's something interesting about this, right? Normally in machine learning, particularly reinforcement learning, what we do is we build a reward function in the future. We basically also run forward in time, and then we say, okay, I have here a reward function that gives rewards to the state where I am in, and I want to maximize the reward. The one problem with that is that for every task that I have, right, I need to come up with well, what is my reward function? I have to design that reward function. And in this framework, and I basically brains cannot afford to, for every problem, to come up with a new reward function. We have thousands of problems every day. So in this framework, there's only one solution approach, no matter what the problem is. You minimize your free energy, or if you want to make decisions, you minimize your expected free energy, and that's all you do, no matter what the problem is. If you don't have a good model for the future, that leads to explorative behavior, that leads to learning the model about the world. If your model works well and you set you have good priors on future observations, it leads to exploitative or utility-driven, goal-driven behavior, and you will take actions that fulfill your goal. And but the crucial thing is there's no reward function. There's just free energy, no matter what the problem is, and that's very powerful about this approach. Okay, so if that answers the question, then I'm going to the next question. If not, just ask me
Yeah,
again. Okay.
yeah, yes, it's clear. For me,
Okay.
it was more a practical sense. How do you searching? So
Yeah.
you mentioned you can turn your head and you make a new observation, and that's, yeah, that's
The
my
big
misunderstanding
the
about it.
big thing here is that so as we, I mean, agents like ourselves, by making actions onto the world, we can change our observations and we can thereby select our own data set. The big question in machine learning is always, where do I get my data set? Well, we just select it ourselves. We go out and if my model isn't being trained well, I will go around, I will make actions that are really have to, that will select the most informative data so that I can train my model of the world. And I don't have to do anything about it aside maybe from making the actions, but it's not there's nothing special about it, right? I don't. So the data set, we also optimize selection of the data set, um, and it's completely built in the framework. That's the nice thing about it. Yeah, Sveta.
Hi. So I still am not very clear with the diagram before this, which explains the whole idea of how we can model an intelligent system. This diagram, yes.
Yeah.
So I do not get how we do the generative part and the inference part. I think the inference part you explained again when you were answering Gautam's question, so that's okay. But I'm not able to tie the two together.
Okay. So the first thing is this is a bit cartoonish, right? The real graph runs forward in time, right? And so it's actually a thing that has some temporal thickness, right? And I don't draw that here, so you don't see any time. So it's a bit inaccurate. You should really see it more as what is the idea? The idea is that inside an intelligent agent, such as the brain, but also a synthetic, right? And if we want to build a robot, what you should do is you should build a model for how the world works, how the world basically evolves, right? There's a state space model, and that state space model generates observations depending on the sensors in your robot. And depending on the actuators in your robot, you can influence that process. And so rather than building a model from observations to the next action, really how it should work and how it works in the brain is the model is the other way around. The model works, let's say, in the generative direction. It tries to generate observations from actions through internal states and observed states. And so if we run this model, it runs in both ways, right? We will predict the future by running it forward in this way. I'm at ST and then I run it forward and I create XT plus 1 and I run it forward, create XT plus 2 and I run it forward, XT plus capital T. And then I run it backwards. Then I have here a prediction of the future and I have a probability distribution about where I want to be. And now I run backwards, right? I run backwards, backwards, backwards to here. So in this cartoonish thing, we run forward to predict observations, then we actually get observations. There may be a prediction error. And that prediction error, as you remember from Kalman filters, that leads to updating in the system. And we do that by just by inference, right? We just infer we do perception from your observations. So that is your state of the world, or your perceived state of the world. And with that, we can infer the actions that would lead to this state of the world, that would lead to observations. But we are mostly interested not in for the use. We're interested in desired observations, in the goal prior here, right? So you go from goal prior, you infer. Let's say this is where I want to be in the future. Then you infer the states that are needed in the world, your perception that you want to see in order to generate this this particular goal observation, and then you infer what are the actions that are needed to get the world in this state. So the inference runs in this way, from up to down, from let's say from X to U, but predicting the future runs in this way. I can run this model in both ways. So there's a generative direction and there is an inference direction. And does that help a bit?
Just to clarify, so then once I make the observation, I try to kind of update my prior about what I would be observing, and then that helps me model the state, the world state, and then come up with what is the action that I need to do next. And in order to predict the next timestamps, in order to predict what I might next observe, then that's where we do the generative part. Is my interpretation correct?
I think so. I think so. It's the updating of these red blocks of where you want to be is not done by this internal system. It's done by another agent, let's say a higher level agent. I mean, at the highest level, we have, let's say, our desired next state is to stay alive, right? At one level lower, that means the desired future is that my temperature remains around 37 degrees, that my glucose level is at certain levels, etc., etc., right? And so you go lower and lower and lower. So and at some point, this module may be, let's say, very low. And okay, so then let's say these desired states are generated by higher level agents, sort of in a descending fashion. So it's another agent that generates this. What this model does, it tries to predict the future. And basically, then you have a, let's say, top down from the model, you have a prediction of what the future will be, what you think the future will be. And then you have from another agent, a higher level agent, well, this is where I want to be to stay alive, right? I want to keep my temperature as 37. So that mismatch between your prediction and where you want to be generates a prediction error. And if you just do free energy minimization in this graph, that leads to, as long as there are prediction errors in this system, that leads to new actions. And you can think of that as that what this system tries to do is to basically run the prediction error to zero, right? There's an external agent that sets where you want to be, and I will make actions to try to fulfill that prediction. That's all that's going on, right?
Okay, so then the generative part is by some high level agent.
The generation of the red
The
red squares of where you want to be is by is by a higher level agent.
Okay.
So the prediction of the future is really by this model, and also inference on what is the next what's the next action is by this model, but it connects to these prior states. You can think of these prior states, let's say these priors on future observations. That is in a sense it replaces the reward function, right? This is where you want to be. That's what you want to observe in the future, and we will take actions to try to fulfill our let's say our targets, our goals.
Right. Okay. So, so the inference is mainly to understand what our next action would be, and the generative aspect is basically to generate what the future prediction, what the future state would be.
Yes, exactly.
Okay.
That's 100% correct.
Okay. And based on what we actually observe, we try to update the state and then see, okay, so there has been a mismatch, so which means I need to change my action, and I do an inference, and then for the next time step, I would say, okay, so so now I've updated what the action should be, and based on this I'm going to make a prediction. Can I still minimize that mismatch?
Yeah,
that's how the loop goes. Okay.
yes,
Yeah,
yes.
thank you so much.
So I mean, let me just say something else here about let's say the relevance for algorithm design, because in the end we are engineers and we want to build algorithms, good algorithms, right? Or good so let's say you want to build a speech recognition algorithm, right? So how does it currently work? Well, you go to the literature and then you see there's about 50 years of efforts by signal processing engineers to build speech recognizers and just algorithms for speech recognition. I mean, it's not like building a low pass filter where you have a very clear criteria and then you minimize it and you get your optimal low pass filter with minimum ripple or something, right? This is speech recognition. It's much more complex. We don't really have a good way of doing it, so it comes down to your creativity, and there's 50 years of literature with all kinds of creative ideas. Currently, it turns out that, well, just throw a big neural net to it, and that's the best approach currently. Once we have an algorithm, then the algorithm has usually a lot of parameters, so you need to train the parameters. And that's the domain of, let's say, machine learning engineers. So you collect a big data set with lots of speech and lots of labeled speech, so it's classified, and you throw it in your algorithm, and then you train the parameters. And then you need to run the algorithm, and then, well, it needs to be programmed, so you need a good, the big systems, good software engineer. So you have three different disciplines. There is this signal processing engineer with lots of knowledge about what a speech signal looks like. You need your machine learning guy or woman that knows how to train these systems. And then you need a software or even hardware person who can implement that. But the brain is, I mean, apparently, I mean, has a very good speech recognizer. How did it happen, right? I mean, I recognize speech and I didn't recognize it when I was born. So it just happened, right? And so what the brain does, and let's say that there is at the highest level that it is beneficial if we can communicate with each other, right? That if you produce a signal that I can actually understand, right? Let's say that we can encode that as something that is desired, right? So then the brain makes this generative model for all the signals we get in, and that includes speech signals from other people. And state inference in that model that you have would lead to estimates of the words that you say. So that's really speech recognition. So we have a dynamic model in our brain for how speech is generated, and state inference in that model leads is basically your classifier. Now, in the beginning, that doesn't work very well. So you go one step higher and you say, well, then we do inference over the parameters of my generative model. And that yeah, in engineering we call it machine learning, but here in this framework is just, yeah, it's just inference over variables, over latent variables. You can call it machine learning, but it's just free energy minimization over the parameters of my model. And you can take it a step further. Let's say in the brain, we also change the structure of the network, right? I mean, during our lifetime, but also by, yeah, creating new people, right? So, but even during the lifetime, the structure changes. You can think of structure changing the generative model structure as the algorithm design, because that, I mean, that changes the equations. So how does the brain do it? Well, free energy minimization. In the end, there's only one force. We do free energy minimization over states, over parameters, over over structures that leads respectively to I mean to building the algorithm, to estimating the parameters, and to actually running the algorithm, to doing recognition. So everything, you don't need 3 engineers. There's just one process, free energy minimization, that takes care of the algorithm design, of training the parameters, of running the inference, of running the recognition system. So that's a lot a lot simpler. You don't need a really big expertise if you know how to do free energy minimization in networked, well, in these graphs, right? And so the idea of, let's say, of artificial intelligence, in my idea of for the future of AI is to move towards that direction, right? To no longer consider algorithm design as something that requires all this creativity from an engineer, but just consider it free energy minimization over model structures. And machine learning, training the parameters, yeah, you need a data set. Well, if you have an agent, the agent will collect its own data set. So you just throw it out in the field, and if the model hasn't been trained yet, it will fly around and try to find the data that it needs to train the model, right? And all of this is under the, let's say, the high level goal that that we understand each other, that we can communicate information, because that helps us survive in the long run, right? So that's something on a very big scale, but in the very small scale, it may lead to speech recognizers. So that's, I mean, it's very roughly and qualitatively the idea of how we can develop algorithms for vision and for speech recognition, for making decisions, for everything, right? There's just one force, free energy minimization, and an overall goal to maybe to survive, right? And so that's a very interesting idea, I think, and that's I think where we see a movement in AI, that this is where the future may go, but it's, I mean, these things go slow, right? But it is very relevant to the idea, I think, of what we as engineers do, right? Engineers, we want to design algorithms. Now we do it really only in a feed-forward way, based on creativity. But in the end, the brain does everything just by free energy minimization. It's not very creative, but it works, right? Okay, a new question by Mike. Go ahead, Mike.
Hi. For me, it's not completely clear what's meant with the uncertainty in a certain state. Can you elaborate on that? So.
Yeah. So let's say that what you do is you make predictions for a state. I mean, let's say the world here is in a certain state, right? Let's say that I look outside and I see a car driving there. Well, that car happens to be at a particular position at a particular time, right? I make an observation, but I don't see all too well because of old age and for whatever reason, maybe misty or whatever. So I get some kind of I get a bad observation, and my model of how the outside world is also not all that good, right? So my posterior over S of t may be quite a broad, let's say Gaussian, right? I may think, yeah, it's a particular location, but there's also very high chances here, and there's also very high chances here. So if I have broad posteriors over my states, that means I still have a lot of uncertainty what the state of the real world is. The real world is in a particular state, but my state of knowledge is vague about it. That's what I mean by uncertainty. And that is due, well, if I would have a very, very accurate model, right, then I basically I can make more accurate predictions, right? And it would also help if I can make actions to make better observations. For instance, if I'm really interested in the location of this car, it would help if I get a little closer, right? If I get binoculars, right? Or I can make actions to make my observations more accurate. And that would also help my knowledge about the state of that car, or the position of that car. So there's two ways to improve, let's say, the uncertainty about my perception, namely get a better model and get better observations, and making better actions.
Yeah, thank you. That's
okay.
More.
Okay,
And,
super.
One small question, and are the states of the model also dynamic? So can they be changed by the actions we take by the agent, or are they stationary?
No, they can. I mean, they can be totally. It can be. I mean, the world is non-stationary, right? So that just in our model, that means that we're going to have to update parameters in our model online as well, right? I mean, let's say that the states is your perception of the world, but hey, if the dynamics of the world, if they change, that I mean that translates in our model that we have to update our parameters, and maybe even the structure of the model. Maybe if something big changes in the world, well, then I just don't have the good model, so I need to get another model. And so but this model will keep making bad predictions. So over time, you will get so many prediction errors that it will actually have an impact on updating parameters, and later on, even on updating the structure of the model. Because there's only one thing going on. The model tries to minimize prediction errors, right? And that can be translated to, that's the same thing in a way as minimizing free energy.
Yes, thank you.
Okay. All right. I don't see any questions at the moment. We're also about an hour into it, so perhaps this is a good moment to start. Let me take, if there's another question, please just let me know, right? Because I want to really address your questions. But I thought your questions were really good. This is a difficult topic, and I'm not going to ask at the exam really quantitative things about this framework, right? I'm happy if you understand a little bit about it. If you got a look at, it's optional, but there is a nice article that I recommend that you read about basically about Carl Friston, who is the sort of the leader of this movement. And it will also say, this is Carl Friston, it will also say in this paper that this is a difficult theory to understand. There's, I mean, there's loads of people that are very good in their fields, and they just have no idea what Carl Friston is talking about, even though they tried hard. So I don't expect you in one, I'm just going to go back, in one class or one lecture to understand the intricacies of what I'm talking about. I just, in a sense, the reason why I include it is just to make you, hopefully to make you enthusiastic about it, to make you believe that, hey, it might indeed be possible that this generative modeling, this Bayesian approach to what we've been talking about in this class. And admittedly, we haven't done, let's say, the examples yet, also not written code, to build big speech recognizers, right, as you can do with a neural net. But if you have a neural net, then well, you have to come up with your database. And what we are, the tools that you actually have now in this class, in principle, are sufficient to build intelligent systems that will collect their own data, and that will and I will do so in a purposeful way, right? It will collect the data that is needed to train a model, and then it will use the model to infer whatever you want it to infer. So everything, in a sense, is automated. It's and the details are difficult and not completely worked out in nice books and papers. I mean, it's rapidly changing, but I think this is I hope you can see sort of a glimpse of why this is an exciting development. Also for engineers that want to build big systems, because in the end, there is actually here sort of a pathway to making the design of a speech recognizer a completely autonomous endeavor, right? You can be, the idea would be you build a generative model for speech or for acoustic signals and you throw it out in the field, and just like a brain, it may move around, it may set attention to certain speech signals and thereby collect the database that it needs to fulfill a particular task. So that's sort of the, so it can become very advanced very quickly, and we don't have time in this class to do it, but I hope you kind of get an idea that I didn't use any additional tools that we already discussed, namely just build a generative model and do free energy minimization. And that's the only tool I use here. And hopefully you kind of see that that can, that can lead to intelligent behavior, making intelligent actions, both searching and goal-driven behavior. If you get that idea, then I think, well, the objective of the class has been reached, right? So there's no more prediction errors from my viewpoint. And yeah, so with that, I think I should stop the recording, unless I still see something in the chat. Let's see. Okay, so there's Magnus. Yeah, so Magnus is a TA in this class, and he has a neuroscience background, so he really can talk through this story in a very interesting way, also from the neuroscience perspective. And I think I really recommend it. And so that will be next Friday. So please join that session. That's going to be very interesting. Okay, then I'm going to now, let's see, stop the recording. Yeah.